In this video, we're going to introduce what's known as a quadratic form. So let's assume that A is some n by n symmetric matrix. The fact that it's symmetric means it has lots of nice properties. Its eigenvalues are all real numbers. It also has the property that it has a symmetric factorization. And let's assume that x is some vector in Rn. A quadratic form is something of the form then x transpose A times x. Now x is n by 1. A is n by n, x transpose would be 1 by n. So this product, 1 by n times n by n times n by, times 1, is actually a scalar. So just to take a look at a simple example, A is 3, -1, -1, 3, and x is the vector 2, 1. You notice that this is a symmetric matrix because these two entries are the same. It happens to be in this case that the diagonal entries are the same. That's sort of coincidence. I mean, I could have a 2 and a 4 here, or as long as these two numbers are the same, this would still be a symmetric matrix. So let's take a look using this particular x, what x transpose AX would be. Here's x transpose, here's A, and here's x. Matrix multiplication is associative, so I think I'll multiply this 2 by 2 times that 2 by 1 first. Doing so, I have 3 times 2 plus -1 times 1. That gives me a 5. -1 times 2 is -2, plus 3 gives me a 1. And now I'm going to take the dot product of 2, 1 with 5, 1, and that's going to give me 11. So this is an evaluation of the quadratic form at the vector 2, 1, but we could do the same thing in general. In fact, we could get a general formula for the quadratic form. So let's suppose now that x is the vector x1, x2, and let's expand x transpose x. We'd have x1, x2. Here's our matrix, 3, -1, -1, 3, our column vector x1, x2. Multiplying this matrix by x1, x2 gives me 3x1 minus x2 minus x1 plus 3x2. So then I multiply this 1 by 2 times this 2 by 1. And I get this x1 times 3x1 minus x2, x2 times minus x1 plus 3x2. This can be simplified considerably, and I have 3x1 squared minus 2x1 x2 plus 3x2 squared. If you've seen some multivariable calculus before, you may recognize this as a function of two variables. If we graph it, it is in fact a paraboloid opening up. It has a graph that looks like this. Let's take a look at another example. Suppose A is -3, 1, 1, -3. X is x1, x2. If I do a similar expansion, I get minus 3x1 squared plus 2x1, x2 minus 3x2 squared. If we graph this, it would actually be a paraboloid opening down. And finally, if A is -3, 1, 1, 3, so it's different than this matrix and the one we started with. An expansion would yield -3x1 squared plus 2x1 x2 plus 3x2 squared. This is an example of what's known as a saddle. So if you've taken multivariable calculus, you may have seen this type of graph before. What if A is 1 by 1? That would be the simplest, the smallest matrix we could have. In this case, our quadratic form, x transpose AX, x would be just a scalar, A would be a scalar as well. So we'd have x times A times x, which is AX squared. And depending upon the sign of A, we could have a parabola opening up or a parabola opening down. What we want to do is we want to be able to classify quadratic forms in the same way that we can classify parabolas as opening up or opening down, or those previous examples as perhaps opening up or opening down or being saddle shaped. And that's where our new definition comes from. It has to do with positive definite, negative definite, and indefinite quadratic forms. So a quadratic form is positive definite provided x transpose x is greater than 0 for any vector x in Rn such that x is not the 0 vector. If x is the 0 vector, this would all just collapse to be 0. A quadratic form is said to be negative definite provided x transpose ax is less than 0 for all vectors x in Rn such that x is not equal to the 0 vector. So a positive definite quadratic form in one dimension would simply mean a parabola opening up. A negative definite would simply be a parabola opening down. In terms of our surfaces, a positive definite would be a paraboloid opening up. Negative definite would be a paraboloid opening down. An indefinite quadratic form is one for which we can have x transpose ax be negative for some values of x, but positive for other choices of the vector x. And this, an example of an indefinite quadratic form, would be the saddle that we looked at a moment ago. Let's take a look at an example. Going back to 3, -1, -1, 3, x transpose ax. We expanded this and we got the following. Now the graph of this was a paraboloid opening up. So intuitively, it would make sense that this is a positive definite quadratic form, but we can see that a little bit more explicitly if we actually manipulate this algebraically. I'm going to break 3x1 squared up into 2x1 squared plus x1 squared. I'll do the same thing here, and then I've got my minus 2x1, x2. x1 squared minus 2x1 x2 plus x2 squared can be rewritten as x1 minus x2 quantity squared. So I've got 2x1 squared, 2x2 squared plus x1 minus x2 squared. Because all of these items are squared, this will be greater than 0 unless x1 and x2 are both equal to 0, in which case x would be the 0 vector. And so that tells me then that this quadratic form corresponding to this matrix is positive definite. Let's go back and look at minus 3, 1, 1, 3. That's a minus 3 right there. A few moments ago, we saw that this corresponded to a saddle. When we expand x transpose ax, we saw it was minus 3x1 squared plus 2x1 x2 plus 3x2 squared. And we can actually make this quantity positive or negative. For example, let's suppose that x2 is 0, in which case this goes away and this goes away. I have minus 3x1 squared, and as long as x1 is not 0, this quantity will be negative. On the other hand, if x1 is 0 and x2 is not 0, this will go away again, and I'll have 3x2 squared, which has to be greater than 0. So unless x2 is 0, so I'd have x transpose ax greater than 0. So this quadratic form is actually an example of an indefinite. Is there, the question now, is there a systematic way that works in Rn? This is sort of ad hoc based upon graphs and algebra. And the answer is yes, and it's based upon the eigenvalues of A. Let's recall some important properties about symmetric matrices. Well, one of the most important properties is that a symmetric matrix has a symmetric factorization of the form A equals QD Q transpose. The matrix D is made up of is a diagonal matrix made up of the eigenvalues of A listed along the diagonal. Convention is that we usually list these in decreasing order. And then the matrix Q is an orthogonal matrix. Its columns are the eigenvectors corresponding to the eigenvalues, which have been normalized. They're all unit vectors, and they are pairwise orthogonal. In the case that we have a repeated eigenvalue, that means we have a two-dimensional eigenspace. The basis for that eigenspace has to be converted to an orthonormal one using Graham-Schmidt. On the other hand, if all the eigenvalues are different, you just take an eigenvector corresponding to each eigenvalue and normalize them. So this is our matrix Q. The vectors u1 up through un, they form an orthonormal basis for Rn. Q transpose would be the transpose of each of these column vectors, and we stack them on top of one another, u1 transpose all the way down to un transpose. So here's our quadratic form x transpose ax, which we can write as x transpose q d q transpose times x. Now let's take a look at this. We're going to introduce a change of variable. We're going to define y to be q transpose x. In this case, Y transpose would be Q transpose X transpose. And when we take the transpose of a product, we take the product of the transposes in reverse order. So this would be X transpose times the transpose of Q transpose, which is just Q. So let's take X transpose Q and replace it with Y. So X transpose AX is Y transpose DY. Let's think about what this is. Let's suppose that Y has components Y1 up through Yn. Here's my matrix D made up of the eigenvalues. And Y transpose would be the row vector Y1 up through Yn. Now let's expand this and see what happens. Let's take a look at this product. If I take the dot product of this row vector with the first column vector of D, because I'm going to have a lambda 1 there followed by a bunch of zeros, the only thing that's going to be left is Y1 lambda 1. When I take this row vector and take its dot product with the second column vector, because there's only a lambda 2 there and the other entries are 0, we'd have lambda 2 y2, and so on and so forth down the line. The last dot product would be this row vector dotted with this column vector, and the only thing that's going to be left is lambda n yn right there. And now I'm going to multiply that by the column vector y1 up through yn. So I'll have y1 lambda 1 times, y1 times lambda 1 times y1 again. That would be lambda 1 y1 squared plus lambda 2 y2 squared, so on and so forth down the line. So this is going to simplify to be just the sum from I equals 1 up to n, lambda I y sub I squared. Now, because of this squaring right here, this term has to be greater than or equal to 0. Let's take a look at a case when all the eigenvalues are greater than 0. So that means that this expression, this sum, has to be greater than or equal to 0 unless y is the 0 vector. But if y is the 0 vector, we could use the fact that Q transpose is invertible and therefore show that x is the 0 vector. So in other words, if all the eigenvalues are greater than 0, X transpose AX would be greater than or equal to 0 unless X is the 0 vector. That would be a positive definite quadratic form. Let's look at another case. What if all the eigenvalues are less than 0? If all the eigenvalues are less than 0, this expression right here is going to be less than or equal to 0. And it would equal 0 only if the vector x was equal to the 0 vector. We'll put a positive there. So let me just say that again. In the first case, all the eigenvalues were positive. This quantity would be positive unless y was the 0 vector, but that would mean that x was the 0 vector as well. Similarly, if all the eigenvalues are less than 0, this quantity will be less than 0 unless y is the 0 vector, which again means x is the 0 vector. Now in the third case, some of the eigenvalues would be positive and some would be negative. What we can do is, let's say we look at the eigenvalues that are positive. We could set the y's, the y sub i's corresponding to them, all equal to 1, say, and the entries of y equal to 0 corresponding to the set to 0 the entries of y corresponding to the negative eigenvalues, in which case this expression would be positive. We could also, for example, look at all the eigenvalues that were negative, set the corresponding components equal to 1, and for other components set them to 0, and this expression would be negative. So depending upon how we choose the entries of y, we could make this expression positive or negative, which means that we would have an indefinite quadratic form. So to summarize all these results, the matrix A is symmetric. Let's assume that. The quadratic form X transpose AX, it's positive definite if all the eigenvalues are positive. It's negative definite if all the eigenvalues are negative. It is indefinite if the eigenvalues are of mixed sign. As an example, 1, 3, -1, -1, 3. We saw before that this is a positive definite quadratic form, corresponds to a positive definite quadratic form. The eigenvalues are both positive, they're 2 and 4, verifies that fact. -3, 1, 1 minus 3. Now the eigenvalues are -2 and -4. That means the corresponding quadratic form is negative definite. -3, 1, 1, 3. This was the case of our saddle. The eigenvalues are plus or minus 3.16. The mixed signs indicates that we have an indefinite quadratic form. Here are some examples for you to try. Here's a matrix: 7, -6, -5, -6, 18, 6, -5, 6, 7. Okay, let's just do a quick check, and this is in fact a symmetric matrix. Let's suppose X is the vector 1, 2, -3. Calculate X transpose AX. Now let's suppose A is the matrix 1, 3, -2, 3, 2, 2, -2, 2, 2. And X is the vector 5, 1, -3. Calculate X transpose AX. And then classify each of the quadratic forms X transpose AX using this A and using this A. Classify each of them as positive definite, negative definite, or indefinite.